Who made the trade? Brewer cat. It's moving. Yeah. That's serious. Simcoe. Simcoe. Oh.
All right, first round through. Now we're going to go all the way back and do a quick round, 15 seconds apiece.
Not mine. Say whatever that photo is not great. Have we tried messing with the
pictures aren't really showing much.
Oh yeah. That's untethered. That's not orange. We need help with trivia.
Obviously AI.
Why is for?
Hold up.
I touched something.
Yeah. Had you fooled for a second? All right, we won't touch it again.
It just appears on the dog.
That's a live mic, Tobin. That's a live mic. Yeah, stop recording. Stop recording. Reschedule. It's never happened.
Man, this beer is delicious.
You're lying, because I got the same thing last time.
I've been so stressed out about the
trivia sheets and golf pencils. We're running low. I promise we're going to get pens eventually. But please come turn them into Chester. Wrong with this thing. Okay.
Hey, Sam.
Yeah.
You should ask her if she wants to hold mic or if she wants to use the stand.
Yeah.
If she wants to use the stand,
Okay. Are you more of a hold mic and walk around person, or do you want to stand by the stand? Okay, okay. Whichever you want. We just like the stand is acting wonky, so we'll go fix it if you want to stand by the stand. Whichever you're more comfortable with. Whichever you want.
ignorance is bliss.
Normally we use
Plausible deniability.
a projector that has a lot of trouble with reds, and we found a different one.
Okay.
Yeah.
And you,
Yeah.
Standard.
She said she can walk around. Do you want to walk around? Or, yeah, walk around. We're going to walk around.
Trying to get a test run.
start on.
You just missed trivia.
I just missed it.
Yeah.
I thought it was a late.
If you won, I don't think we'd have given you a prize.
But if you come over, maybe I'll give you an Astro on Top sticker just for fun.
I will.
Yeah, absolutely.
Okay.
Top should start 7:30. Yeah.
Are we ready? Who's Steph? Who's Steph?
You get a focus.
I don't go to things anymore. Okay. 6.
Go discover transit time
Okay. Well, let's go do the one we'd all gone boo.
She found it AFC, like the original.
Who?
Meg Swan.
Oh, very cool.
She and Emily Rice did the first.
Ah, yes, Emily. Cool. I'll start fast here. Okay, are you all ready? Good. Okay, I'm gonna go introduce you. Woo, hello. We are ready to get started. Once again, I'm Sam, standing in for Megan, and we've got a stellar team lined up for you today. Starting us off is Kathleen, or Kiker. Yes? Okay, amazing. I did not check that beforehand. Bad host. But yes, Kat is a part of the ADAM software engineering team, and her prior research is focused on black hole formation using cloudy simulation software. She previously worked at Lockheed Martin and led the development for latest releases of large-scale Fortran and C++ physics modeling code to run on high-performance computation computers. So she's a badass and really smart. And her current stuff, which she's going to be talking about, has to do with asteroid impacts. So I'm going to just hand it over and stop babbling. Here we go.
Oh, yes, thank you. And thank you to the organizers for letting me come and yap about my favorite subject in the world. Let's try this out. Oh, there we go. Okay, so I work at the Asteroid Institute. It's an organization founded by B612, which is a nonprofit that whose goal is to prevent an asteroid impact to the Earth. So one of the main ways they do that is by hiring a software team that builds tools like the Atom platform, that are open source and available to everybody, so we can all do some science together. So really quick, this is our team. These are our fearless leaders. Oh, sorry, point at this. Clearly. And this is the software team. And everything that I talk about today was a group effort by everyone up there. Okay. So. Okay, so there was an asteroid in the news recently. I don't know if you've heard about it. It's always nice to see your subject of interest be in the news, but not always quite like this. So in late December, the asteroid 2024 Wainer 4 was found by Atlas, and it registered a small possibility of hitting the Earth. And that possibility stayed below 1% right up until January 29th. When it crossed that threshold into 1%, at which point the International Asteroid Warning Network and others began to take notice in a more sort of intense way. And then, so a lot of the times you will see asteroids will register an impact probability, and then really quickly we'll all get telescopes on them, and it'll drop to 0 within a couple days. This one was a little different, and it actually kept going up little by little right up until about February 18th, when it peaked at 3.1%, which was the highest for any asteroid of its size that we have found so far. But as these things often do, by February 21st, that impact probability started to drop for the first time. So the chance of Earth went down. And then by the 23rd, that impact probability had rapidly dropped until it was basically 0, and we could consider this thing no longer a threat. And then finally, some of the last observations we're likely to get of this object were by JWST in March. Okay. So what is this object? I'll give a little introduction to it. This is 2024 WIRE-4. Some of the reasons why it kind of captured people's interest and our interest along with that. It has an impact of in 2032, so only 8 years after it was discovered. So it's enough time to potentially do something about it, but it's not, this is gonna hit maybe in 50 years. So that kind of grabbed people's interest. Also, it was around 40 to 90 meters in size, which is pretty big. Again, kind of in this middle zone, not quite an existential threat, but also, not nothing. And to give some context for that, you can see on the right some different sizes of asteroids. And for example, let's see. So this is Chelyabinsk, the asteroid that airburst over a town in Russia. That's about 17 to 20 meters in size. And for something a little closer to WIRE-4, this is Tunguska, also Russia. And this flattened an area of a forest to the point where even today trees are not growing there. And that was about 50 to 80 meters in size. So if you compare that, WIRE-4 was about the same size as Tunguska. So something that we like to, or people often called a city killer asteroid. So it's not going to end life on Earth. It's not going to make anything go extinct, most likely. But you do not want this coming anywhere near you. So, okay. Yeah. Additionally, things that made it interesting, like I said, it approached at a shallow angle. So it kind of is coming straight at us. That means as we get more observations, we're not really able to pin down the orbit as well. And that's kind of why it hung around in that low impact probability zone for a while. And it was visible to ground-based telescopes up until about April in 2025, being nice. And then not again until 2028. So what that meant is if we did not get that impact probability down to 0 before this went out of view, we wouldn't know what was going to happen until it was kind of too late to do anything about it. And then, like I said, JWST had a follow-up to determine its total size. Let's see if this works. There we go. Thanks. Okay, so how do we get here? What is the timeline of an impactor like this? Well, like for any asteroid out there, it's going to start in observatories. In this case, it was Atlas, but for other objects, it'll be other observatories. They'll be looking at the sky all night, and along with all of those stars and galaxies that I think you'll hear about later, there'll be small moving points of light, and those are probably asteroids or other small bodies like comets. And so they will gather up those observations, they'll link them, and they'll send them to the Minor Planet Center, which is like the clearinghouse of asteroids. So all over the world, observatories are sending all of those observations into the Minor Planet Center. From there, then JPL and Sentry on the NASA side, or for the ESA side, NEO-CC, they ingest those observations, and they're looking for anything that might be a threat. So anything that's a near-Earth object, that's the NEO, and particularly anything that has any kind of chance of hitting the Earth. So as these observations of 2024 WIRE-4 went into the Minor Planet Center, both of these bodies would ingest those, determine that it had a chance of impact, and then they publish both what they believe the orbit is and what they believe the impact probability is. And if you're curious how exactly those two do that, well, so are we. Yeah, so to be fair, it's not like it's completely an unknown. We know basically what they're doing, but things like the weights that they give observations, how they choose which observations to include in their orbit fit, how they do their propagations and impact determinations, those are all not like widely known, not available to anyone to kind of examine or think about. So one of our goals is to try and make those things available to other people. So we want to create tools that are as good as JPL or ESA as a high benchmark, you know, that's the gold standard out there. And we also want these to be fast, performant, and built on modern programming tools so that they're easy to work with and maintain. And so the 3 parts of how you get to an impact probability. The first one is orbit determination. You have these observations and you need to get an orbit out of them. So what is that arc that fits the observations we have, basically? Second is what we call Monte Carlo and the variant creation. Monte Carlo based on a casino. So just like if you, they said if you want to know how a slot machine, how often it pays out, you can study the insides of it, or you can just pull the lever 1,000,000 times and see how many times it pays out. And that's basically the same idea of what we do here. We take an orbit, every orbit and every observation comes with some amount of uncertainty. And so we pick different points within that uncertainty and we say, what if this is the orbit? And then we propagate all of those forward, and if any of them hit the Earth, then that orbit has a chance of hitting the Earth. And so essentially you have, for example, 100,000 variants. If 1,000 of them hit the Earth, then you have a 1 in 100 chance of hitting the Earth. And so those are the 3 main pillars of impact probability calculation. Okay. All right. And so this is where we came in. We have this coding platform that we call ATOM, Asteroid Discovery, Analysis, and Mapping. It's built on Google Cloud, and it ingests observations from a large number of observatories and then has a wide range, some of the examples on the right, of tools that we can use using those observations and this platform. Sorry. There we go. So we wanted to help. The main ways we could do that was by reducing the uncertainty in the trajectory. And the best way to do that is by getting more observations, and also to provide tools that are open source to help better understand this and let people do their own calculations and come to their own conclusions. And so like I said, this is our platform. It's open source, and it also has web-based tools that are available to people. And we collect 14 different instruments worth of point source catalogs, so observations that telescopes have taken. And it runs on Google Cloud, which means it's pretty fast, which is nice as well. Okay, so step 1, the best way to, like I said, was to reduce the uncertainty, to get a better orbit, is to get more observations. The kind of best or most common way to do this is to put more telescopes on the sky and try to see that object again. But another way you can do it is you can go back in time and you can say, was this object seen before we knew what it was? Because there's lots of observations of moving objects that haven't really been linked to any known asteroid out there. And that's essentially what precovery does. We go backwards in time and we look and say, for this orbit, are there observations that have been seen? Like, where should this have been on the sky? Let's look at those images and see if this is where we think it should be. All right, there we go. Okay, and so we did that, but more than you want to help by providing good observations, you definitely don't want to make it worse by providing bad observations. And precovery has a chance of finding something that's not the same orbit. Ooh, okay. Am I stepping on something? Is it okay? Huh. No worries, no worries. I can keep talking if you want, or I can wait.
What's your favorite astronomy joke?
Oh gosh. Okay, it's not really that astronomy, but an infrared photon walked into a bar and it said, "Is it hot in here? Or is that just me?" Okay, yay! Look, you brought it back. Nope. Okay, it's gone again. I won't move anymore. All right. Anyway, I was saying, so you don't make it worse. So you need to know that the observations you found are real. And this is one of the ways we do that. We have this tool that will pull the image so you can look at it by eye. And here on the right, you have examples of what you should be looking for. You see streaks. You see the object is in one image and gone in the next. That tells you it's moving. Over on the right, some things can sometimes trick the programs into thinking that they were moving objects or asteroids, but they're not. Here you have a solar flare, you've got a cosmic ray, and you've got a static object that somehow got registered as something that was moving. So these were the observations we found. They all looked good based on our criteria, and they were submitted to the Minor Planet Center, so that helped to refine the orbit and essentially either decrease or increase based on what the true state is, the impact probability of 2024 YR4. Yeah, go ahead. Okay, so fourthly, I guess, one of the things we set out to do was to provide these open source tools so that people could kind of compare their own results to JPL and ESA while having a better idea of what exactly is being done. So we had this tool available, we had it already existed, and so 2024 YR4 was a great test bed for this. So day by day, as new observations came in, we were able to use our own orbit determination and our own propagation and impact probability calculations and compare them to ESA and JPL. And in general, we found our results were consistent within 10%. Usually they were actually much closer than that. And also interesting, we found that there was about a half-a-day lag between when the observation and state vector would update and when the impact probability would update. And all that really meant was that we would tend to sort of know where the probability was going to go in the official estimation before it happened. So we would see a drop before the official figures were coming out showing a drop. And again, that was a great way to test our tool and really show that it was actually working as we expected. Next. Okay, so as I said, not to bury the lead, but this is not a risk to any of us. It will not hit the Earth. But how bad could it have been if it was? And that's why we generate these impact corridors. Because for an object of this size, if it hits in the middle of nowhere, that's actually not really a big deal. You would get a big crater, you'd get some shiny new meteors that we could study, and that's about it. However, if this were to hit on a population center, that would be catastrophic. And so looking at the risk corridor, we actually saw that it did pass through some pretty major cities like Lagos, like Calcutta, Bogota, and Mumbai. But as I said, fortunately, this is now 0% probability, more or less, so no concern there. All right, now we get to find out if these will play. Does that work? Okay. So why stop there? We decided to make some other just fun visualizations. This one shows the impacts as they come in, going across the Earth. So you can kind of see it's jumping around on both sides. That's kind of if you imagine the uncertainty as like a sheet of paper cutting through this sphere. So it hits at one point and then it starts hitting on both sides as well. And that's just the way that the uncertainty is like this long, thin line as it comes in towards the Earth. So that one was fun to see. Kind of here again, oh, it's a bit dark, so I don't know if you guys can see this, but there's a line of uncertainty as it approaches the Earth. And then you can also see the rotating frame of the Earth as those impacts come in. Yep. The next one. And I think the next one is a similar, but just more zoomed out. So there's the Earth on the left. The orange is what we call the nominal orbit, so the best guess, or like the middle of the uncertainty region. And eagle-eyed people might see there's something right on the edge, but that's fine. If you go to the next slide, we can take a look at that. Because despite the fact that there is now basically no chance of this hitting the Earth, there's actually still around a 4% chance that this will hit the moon in 2032. So yeah, if we play this, you can see the red parts of the line is where it does show an impact of the moon. And you can even see how it kind of perturbs when it gets towards the edges, and that's because close approaches will tend to bend the orbit. And another thing to point out is, again, that orange. If you want to play it again, thanks. So the orange dot there is the nominal orbit, or again, the best guess what we think the orbit is. Of course, anywhere on the line could be the orbit. But if you look how close that nominal orbit is to the moon, what that tells us is there's a good chance that this probability of lunar impact will actually rise before it either falls or we actually confirm a lunar impact, because that is quite close in comparison to how close the nominal ever got to the Earth, for example. All right, next slide. So yeah, asteroids coming towards the Earth and possibly hitting them are never great, but for us, they're exciting because it gives us a great chance to test out our tools. And so we had built all this stuff, and it was an awesome chance to kind of see it working in real time. For us, and I assume for the rest of the asteroid community as well. Next slide. Okay, and a final shout out before I go. So the Rubin Observatory with their legacy survey of space and time is going to come online later this year. I mean, I think it's already online, but it'll start collecting data. And this is predicted to publish over 100 NEOs per night, and up to 60% of those 140 meters or larger over its 10-year survey. And the reason this is important is because, you know, that's a huge increase over what we're currently finding, and we still see things like Wainer 4. So it's possible that when this comes online, we're going to see more and more objects like this, where we start to see a higher probability before maybe it drops, or maybe we actually confirm an impactor before it happens. And you know, that's an exciting time, because as my boss at the Asteroid Institute likes to say, the only thing difference between us and the dinosaurs is that we have a space program. So hopefully that means that we can do something about it if we ever find an asteroid that will hit the Earth. All right, and that's all from me, I think. Yeah, and yeah, please feel free to reach out as well, and then, yeah, I think we can do questions. Yeah, okay, cool, yes. Yeah, that's a good question. We've been kind of probing NASA. I think there was a directive a while ago that they make most of their stuff open source. I know the reason that they didn't is because some of their code had gone through some universities and some private entities, had basically worked on it and helped develop it. And so because of that, they couldn't make that open. Beyond that, your guess is as good as mine. I mean, I think to some extent governments might want to kind of be able to control some parts of the narrative, mostly just to not spark panic is the sort of best interpretation of that. But yeah, that's why we try and do what we do. Yeah. Anybody else? Yes.
Has there been any talk of trying to get 24-wire to actually hit the moon, like all dark?
I don't know if anyone would consider that, but I like the way you think. The question was, has anyone tried to like deflect it so it will hit the moon? I mean, that would be some awesome science for sure. I don't know, that might be a hard sell, but I'd be with you for that. But no, I have not heard of that, yeah.
What's the latest thinking about how we would deal with asteroid activity?
Yeah, absolutely. Great question. What is the latest thinking on how to, like what we do about an asteroid that might hit us? And actually, just later next week, actually, there's something called the Planetary Defense Conference going on, where a lot of people get together and they think and they talk about this. So there was the DART mission recently, which was the Double Impact Asteroid Recovery. Yeah, okay, thank you. Asteroid Redirect. And that was a kinetic impactor. So that was just, you take something heavy, you hit it into it, and you impart a momentum that changes the orbit. And While these things are big, you don't actually need that much velocity to change their orbit enough to have it miss the Earth. Like, you're not completely throwing it into the sun here. You just need to change it a tiny amount so that when it intersects our orbit, we're not there anymore. So that's one way. If that won't work, there is talk of, you can use like a nuclear disruption. So basically try to blow up the asteroid or blow it into smaller pieces that will also probably not hit. So those are the two main things. Yeah, great question. Yes? Only ones that we do, or only ones that people can do for this? Okay, we do lots of different types of simulations. When it comes to impact probability, it's kind of the only real one you can do. I mean, you can do, there's other theories that I'm not as familiar with in the ways you do the sampling, but basically it's such a chaotic situation that there's no way to really solve it any other way. You kind of just have to sample the possible orbits because there's so many gravitational bodies in the solar system. Yeah, it's just too chaotic. Yes. Okay. Yes.
How fast can a meteor go?
How fast can it go?
What's the fastest meteor ever recorded?
I don't actually know that. I don't know. They can go pretty fast, but I don't know what the fastest one is. No. I don't know. Does anyone here? What's pretty fast? So we usually do it in AU per day, so I would have to do the calculation in my head. An AU is the distance from the Earth to the sun. So yeah, I think it's thousands of kilometers per second, probably. Yeah. Okay, somebody's nodding, so that seems right. But my mental math is not great. Yeah. Okay. Okay. Great question. We have the capability to do that. So we actually use the assist propagator, the creator of which is actually here. And that allows a certain number of bodies, but it's basically all the planets as well as, I think, the major asteroids. So we can do collision with anything that propagator can handle, which is currently that list. So we've only done it for the Earth and the Moon, but theoretically, like with our system, you could do it with pretty much any planetary or any of the major asteroids, or sun, too. Yeah. Is this one over here, or no longer? Okay. Good.
Okay. If someone might click it, I'm gonna wait. Oh, where's the marker? Oh, okay. Cool. Okay. Before I release you for our intermission, we must go over the trivia answers. I will say a lot of you are smart, or these were too easy for you. I have a lot of winners here today, but here we go. Okay. Number 1. What is a stellar cluster? It is a group of stars that form together when they are gravitationally bound. Number 2. What is the closest spiral galaxy? I hope all of you got this right. The Andromeda galaxy. Number 3. What triggers the birth of a new star? Gravity causing gas and dust to collapse. Question 4. Why do astronomers study star clusters? To study the life cycles of stars in a shared environment, and because they're cool. Okay, 5. What distinguishes an open star cluster from a globular cluster? Open clusters are loosely bound. Yes. 6. What is an asteroid? A chunk of rock and metal that orbits the sun. 6. Okay. How was an asteroid 2004 Y2 first discovered? Using ground-based telescopes scanning the sky. I love it. Where are the most asteroids in our solar system found? In the asteroid belt between Mars and Jupiter. That makes sense. Even after an asteroid is ruled out as a threat to the Earth, why might scientists still monitor it? Because it might pose a threat to other planets or moons. We just talked about that. Good. All right, 10. What does an asteroid's impact probability represent? The likelihood it will collide with the Earth or another body. Great job, everybody. Okay, now, can I get a drum roll, please, for our many winners? All right, here we go. In no particular order, we have Shaggy. Woo! Good job, Shaggy. Guys, we will get prizes at the end of the second talk. Thank you. Yeah, they got all of them right. Like 10 out of 10. We got some games stepped up here. All right. Second, Mom Spaghetti. Woo! Good job. The Green Piglets. Green Piglet, nice. Wait a second, I see some undergrads over there. All right. I'm suspicious though. All right. Team Jobo. Hey, good job, Team Jobo. You go, Glen Coco. Okay. That's what. Nice. Did I do it justice? Was that what you wanted? I see. Okay. Random Wonder. Random Wonder. Nice. Take a bow. God, we're still going. Plot holes. Plot holes. Nice. Good job, plot holes. And last but not least, cluster chords. Woo, good job, cluster chords. Okay. If you got 10 out of 10 and I just called your team name, please come to me after the end of the second talk to claim your mysterious prize. Thank you. We will release you for about 10 minutes to go get more beer, go find food, whatever you want. And we'll see you in a bit. Hello, hello, hello. I hope you had a wonderful time getting food and drinks and such. But we got to start this because somebody needs some help. And I want them to tell you what's going on. Our next speaker is Tobin Wainer. They're a third year third year grad student. No, you are. Third year PhD candidate recently minted. What else about Tobin? Tobin does really awesome work. So much research happens that Tobin does. Also, great volleyball player. I've poached him to be on our team. And funny story about Tobin, I never get a good picture of Tobin. He's always eating food. And when I'm taking photos, it's comical actually. But I'll stop yapping and let him come up here and tell you why he needs some help. So let's go. Another round of applause for Tobin.
Thanks, Sam. I am here because I need help. How many people are here tonight because they like science? I did not see everybody's hands going up. Slightly discouraging. How many people are here because they have a partner or friend who likes science and then they were roped along for the ride? Okay. All right, cool. Well, as I mentioned, I am here because I need help. That's not just something that my ex-girlfriend used to say. Oh, come on, y'all. You gotta lighten up. I do need help. I need help to finish my PhD, and I need your help to do it. I am studying this galaxy right here. This is the Andromeda Galaxy. The Andromeda Galaxy, as you may know from our trivia, is the nearest spiral galaxy to us, and it is currently the largest member of the local group. I say currently because it is currently on a trajectory heading straight for us. And if we were to stick around for about 5 billion years, the Andromeda Galaxy and the Milky Way will merge to form one Milk-Dromeda Galaxy. But the Andromeda Galaxy is a naked eye object, so if you go outside of Seattle, you can actually see it with your bare eye, which is very cool. It's a very prominent feature in the night sky. So I, unfortunately, am not the very first person to view this galaxy. This galaxy has been viewed for centuries, but one of the most prominent observations was done by Edwin Hubble in 1923, who actually viewed this galaxy and was able to determine that it was, in fact, a galaxy. It was not a member of the Milky Way, and that the universe was a lot bigger than we originally thought that it was. And so the Andromeda Galaxy has been incredibly prominent in our story of where we come from and where we're going. In the last decades since Edwin Hubble made this discovery, there's been lots of images that have been taken of Andromeda, but none have been quite as impactful as a series of images that were taken with the Hubble Space Telescope. And they were taken as a part of this survey called the Panchromatic Hubble Andromeda Treasury, or FAT, P-H-A-T, FAT. This survey was led by Julianne Dale Canton, who is currently the director of an institute in New York, the Center for Computational Astrophysics. She is truly one of the most amazing scientists of our generation. And this entire survey took 13,000 images of the Andromeda Galaxy with the Hubble Space Telescope over a 40-month span. This has been one of the pillars of our observations of other galaxies. In 2012, when this survey came out, we discovered over 1 million stars in the Andromeda Galaxy, which today actually made it more, we discovered more stars in the Andromeda Galaxy than we did in our own Milky Way. And so I'm extremely excited to be here today to tell you about the next step in our study of Andromeda. Not the FAT survey, but the FAST survey, where we're going down to the southern region. So the Panchromatic Hubble Andromeda Southern Treasury, FAST, we love our acronyms, PI'd by Ben Williams, who's my current advisor at the University of Washington. This work is being spearheaded by a postdoc at the University of Washington, Joe Chen, who has been truly an amazing scientist in gathering all of this data, compiling it for this FAST survey. Also, she was very kind and lent me slides tonight. So if you see any really amazing transitions between the slides, we can go ahead and thank her. So the FAST survey is 1,500 images of the southern region of the Andromeda Galaxy, over 195 individual telescope pointings, which took place over 25 months. It's slightly different than the FAT survey, which was in a few more band passes. So we had 6 different filter combinations for FAT, whereas for FAST, because the Hubble telescope is currently operating on a limited basis, and we needed to be a little bit quicker in how we were and more efficient in our survey pattern, we decided to go only 4 filters in the UV and optical, so we were able to do it in about 1/10 of the amount of total images. But with these 2 surveys combined, we have created the largest photomosaic ever assembled of Hubble telescope images. So shown here is the entire disk of the Andromeda Galaxy. Now I want to pause just for a moment and really marvel at what has gone into this single image here. This image, as I mentioned, is over 14,000 individual Hubble pointings. There have been 60 people across 40 different institutions which have contributed to the work of this survey. Each of these pictures is spanning 10 different decades, and now we are able to fully glimpse the disk of Andromeda. In the entire disk, in this mosaic here, which sets the gold standard for what is possible with space telescopes, we have 250 million stars which are able to be individually resolved. When we split these different stars up into their different demographics in terms of age, we can begin to learn a little bit about the structure of the galaxy. Just considering stars that are old, older than 2 billion years, we see a very smooth gradient across the disk. This is reminiscent of elliptical galaxies that are older and redder and don't have spiral arms. However, when we move to stars that are slightly younger, around 500 million years, we can begin to see these spiral arms take place. Now, what's really interesting is this point right here. This is a dwarf galaxy, M32, that at some period of time has interacted with the Andromeda Galaxy. And we don't have great constraints on when this interaction takes place. And we don't actually know how far away it is from Andromeda. However, we see this point here in the old population of stars, and only a very small fraction in the stars that are younger than 500 million years. But interestingly, while over here on the right-hand side, we see this very prominent ring going across the entire galaxy, right where 32 is, or M32, it splits into 2 different rings. 1 ring over here, 2 rings over here. This is evidence of some kind of perturbation that happened to the M31 disk. Now, M32 is right there. I'm not saying it did it, but it probably could have. So these are stars that are younger than 500 million years. But now if we just consider the youngest stars in the galaxy, stars that are younger than 30 million years, we see the spiral arm structure take place again. So when considering all of these different populations of stars within the galaxy, we can see the morphology of the galaxy change as a function of time. So maybe these spiral arms that we're seeing are not super long-lived features of the galaxy. And we can begin to piece together different galaxy evolution clues from studying these different stellar populations. Now, this is really amazing in terms of galaxy evolution. However, if you came to my Astronomy on Tap talk last year when I was here, you would know that I study star formation. So while the stars are forming in this galaxy, I want to know how that took place. And that's one of the reasons why I need your help. Shown here is a simulation that it was done in 2021 by a collaborator of mine, Mike Grudich. So we start with an entire ball of hydrogen right here. it undergoes some kind of gravitational perturbation and collapses to form stars. So each one of these points there is an individual star. So as we start with this enormous ball of hydrogen out in outer space, and it begins to collapse, what's important is that it doesn't just form a single star, but a whole bunch of stars at once. The most massive of these stars are particularly important because of these jets here, which then clear out the entire region of gas and expose the rest of the stars for our optical eyes. So as we kind of rotate around here, we can see these different subgroups of stars. These groups are called star clusters. It's currently not totally known how many stars from a star-forming event end up in gravitationally bound stellar clusters. And that is one of the pillars of my thesis. I want to understand, if you're forming a whole bunch of stars, how do you form something that lives gravitationally bound for 1 billion years? So going back to that simulation that I just showed, this is work that I've done over the last year, so it's not quite as pretty of a movie as I just showed from Mike. But what I've taken is I've taken just the gas particles from that simulation that end up in the gravitationally bound cluster and track just those gas particles through the simulation. So what's interesting here is we can begin to see this formation of massive stars on timescales of about 5 million years. But the influx of gas and the influx of stars boils down to a very small point in the center of the gravitational potential of this massive cloud. So now we have all of our stars that have, or all of our gas that have formed stars. They begin to disperse and are attracted to each other just long enough to form something that will stay gravitationally bound for a long time. And now this object here, which I've simulated, looks something like that image from the Hubble Space Telescope, which I showed just a little while ago. Now, all of this is theoretical. We don't have 14 million years to go stare at a star formation region. So I can't exactly prove that this is 100% how a bound star cluster forms. But one of the ways that we can test our observational theories is by going to observations and directly comparing observations to our theoretical models. And that is where I need your help. I just mentioned this amazing FAST survey, which took 1,500 images in our nearby Andromeda galaxy. In here are some star clusters. I want to know how they formed. And in order to do that, I need your help. Now, the way that we're going to go about this is through a citizen science project. Is anybody here familiar with citizen science or Zooniverse? Awesome. Okay, lots of hands going up. Fantastic. So we did something a little bit similar to this cluster search, which we're going to perform in FAST in the southern region of Andromeda. We did it in a nearby galaxy, the Triangulum galaxy, which is actually a satellite of Andromeda. So in terms of the angular resolution of the telescope, in terms of the number of stars, it's going to be very comparable to what we were studying with Andromeda. So shown here is a photomosaic of the Triangulum galaxy, which we have searched for star clusters. And I'm going to talk you through that project a little bit so you can see behind the curtain a little bit on how the citizen science project works and how we go into actually finding these stellar clusters. So this photomosaic was created by a grad student at University of Washington, Meredith Tobin. And if we zoom in a little bit, we can actually begin to resolve the individual stars. So here, looking at this image, thinks they see something that resembles a star cluster, which I showed in one of the previous slides. I'm seeing some pointing. Come on up. Let's see it. Right here. You. What's your name? Sam. Let's give Sam a round of applause. Amazing. Sam thinks he sees some star clusters. Where's the star cluster, Sam?
There seems like there's kind of more orange stuff over here.
Yeah, I agree.
Maybe a little bit down here.
Okay.
Kind of in the upper left-hand corner as well.
Yeah, for sure. Awesome. What about maybe that guy? Do you think that's some tightly clustered stars?
I'm not sure what the colors are.
The colors are different types of stars. I apologize. I should have explained that. Blue are young stars, red are old stars. So if we're looking for a young cluster, maybe a group of blue stars together would be a good one. I love it. So looking at this image, you think that maybe you see a couple different star clusters, maybe some groups of blue stars over here, maybe some groups of red stars kind of over here.
Yeah, it feels like here too. Maybe
I love it.
in that area.
That's so awesome. Everybody give Sam a round of applause. Thanks for the help, Sam. And that is the Citizen Science Project. We need people to look at these images and try and identify on them where they believe a star cluster is located. So for this project in particular, we had 60 people look at each image and then click on the website where they think a star cluster is located. When we then compile all of the clicks from all of the different users, we had some people that agreed with Sam that maybe there's some clusters over here. We had a bunch of people click in these different regions here. So now we have 60 different people's clicks on this image. And it's usually about this point in the talk where I'm telling people that I need them to look through 2,000 images and click where they see a star cluster, that somebody raises their hand, pushes their glasses up, and says, "Excuse me, Mr. Scientist, can you not train a computer to do that?" I could, absolutely. I could do that. And then I rebuttal, "What's this?" Anybody have a slight guess at what this is? Is this a star cluster? Headlights? No. These are images taken with the Hubble Space Telescope.
Doesn't mean they're not headlights.
That's a great point. If I were to train a computer to look at the images looking for star clusters, it would take one look at this thing and say, "How you doing? Keep it moving, not a star cluster." And I agree, this is not a star cluster. But I don't know what this thing is. It's green, that's cool. Kind of extended, right? There's this kind of funky thing down here, that's pretty cool. And that's exactly what a citizen scientist said when they looked at an image and saw this thing. They said, "That weird thing up in the corner, what's that?" And a scientist looked at it and said, I don't know. And that is how an entire group of objects was discovered. This is a green pea galaxy. It's incredibly oxygen rich, which means that as star formation goes on and photons ionize the region around them, they appear green to us. We had no idea until a human looked at an image and said, "That's weird, what is that?" And that led to the discovery of an entire classification of objects. So yes, I could train a computer to look through all of these images and find all of the star clusters, but then we wouldn't discover anything else in those images besides the star clusters. And so having humans with human eyes look at things is incredibly important. Back to our image here. We have 60 people click on the image where they think a star cluster is located. So now the rest of this little section here is going to be how we go from these clicks on the image to creating a catalog of star clusters that is usable for science. So 60 people have viewed this image, clicked where they think a star cluster is. Let's say I'm one of them, and you are also one of the people that looked at this. Who thinks they're as good as me at identifying star clusters? Not a single person? Really? Okay. Oh, Ashan, okay, you think you're good. Nice. I love it. I think you're right. I think that I have been spending way too many years looking at star clusters, and I think I know what they look like. which means that if I'm looking at this object, maybe my classification should be worth a little bit more. So in order to track individual users and assess how good they are at identifying star clusters, we keep track of user data. We're kind of like Facebook. Each one of these points is a user that helped us with our citizen science project. And this is how we quantify how good you are at performing the task of finding stellar clusters. On the x-axis is how much you agree with other people. And on the y-axis is the quality of object that you clicked on. So in the bottom right-hand corner here, we have these type of users that agreed with people, but they clicked on everything. If there was a star in the image, they clicked on it and they thought it was a star cluster. So people down here, we consider them very, loose with their classification. On the other side of the coin, people up in the upper right-hand corner here, these type of users only click on things that are the highest quality of star cluster. This thing is enormous. It's very bright. We're talking many, many stars. However, they're also going to miss a bunch of clusters because they only click on the highest quality clusters. So the sweet spot in this graph is kind of right in this region here. Most of the things that you click on, everybody agrees is a good cluster. Most of them are pretty good clusters, but some of them are going to be kind of in that gray area between a really good cluster and something that may or may not be a cluster. So I made this graph, right, back in, 2019. Each one of these dots is a user. Who do you think was the very first person I looked up to see who or how good they were at performing this task of finding star clusters? The first person that I was like, I want to know how good they are. Me? Absolutely not. No, I know I'm good. My advisor. The guy who's telling me what to do every single week. How good is he? Yeah, he was really good. Right in the sweet spot. Nailed it perfectly. I started paying a little bit more attention every week. At the end of this project, in the next couple months, once we have fully done this citizen science project, we are going to collect your user data. And if you want to know exactly how well you are at performing the task, I encourage you to find Geo. Geo is standing in the audience, or sitting in the audience right there. You can go find Geo at the end of the summer and say, hey, Geo, here's a $20 bill. How good am I at finding star clusters? I've been working with Geo for a little over a year now, and I just want to take a second because yesterday, Geo was accepted to one of the most prestigious master's programs in the entire country. So let's give Geo a huge round of applause for a very well-deserved acceptance. And I'm very excited that Geo's going to continue working with us through the summer on this project. Great, so as I mentioned, up and to the right is typically better at performing this task of finding star clusters. We find that as you continue through, as the more classifications that you do, the better you get at finding star clusters. We are very growth mindset over here at Citizen Science. So colored on this part are groups of users based on the number of classifications, and you can see that as people go a little bit further, they get better at this task. The grayed out region here marks the group of users that have not performed enough classifications to receive their own weight. So ultimately, we are going to give every single person a weight on how much their contributions contribute to the project. If you are really good at the task, your contributions are worth a lot. If you are not good at the task, thank you so much for participating. Very much appreciated. Your contributions are very well valued, just not quite as much as the next person. In order to have an individual weight, we need people to have a Zooniverse ID, log in so that we can track who is performing the classification. And you need to perform at least 25 classifications. And we came on this number for a few different reasons. One, just simple number statistics. The second being, you heard about this really awesome citizen science project at a brewery, drinking a lot of beer. first couple classifications, maybe not the highest quality classifications. But after you get it past 25 classifications, then we have enough number statistics to robustly give you a weight. So each individual user, their clicks have a weight attached to them, and then we can begin to look at the image and create our catalog. This is a plot which demonstrates the robustness of our weighting scheme. So me and my advisor went through about 500 clusters, kind of in this gray region between good and bad, and ranked them according to what we thought. The blue points here are things that we said were bona fide star clusters. The red points were things that we said were crap. You can see that the blue dots in general, on the x-axis here is the original fraction of users that identified that, and then on the y-axis is the weighted score that object receives. So in general, once we apply our weighting, the blue objects move to the top, and the red objects move to the bottom, so our weighting system is working pretty well. Great, so coming back to this image, we had 60 people click. We go all of this behind the scenes data, or behind the scenes ghostwriting and stuff to make the weighting system, and now we are finally able to come to a clustered catalog. So these two objects here were identified to be good quality clusters, and this guy, even though it has a chance, it's going to go in the backup catalog in the appendix of the paper that is a candidate. One of the important aspects of this project is being able to quantify the type of stellar clusters that we are finding. One of the ways that we do this is by actually injecting synthetic clusters into the images where we know the properties intrinsically, and then we get an exact reading on what type of clusters are injected. So shown here is an image where there's not a ton going on. You know, we have a few bright stars that some people clicked on that they thought maybe were clusters. And we inserted a synthetic cluster. Everybody found it. Nice big synthetic cluster. Not all of them are going to be this big, bright, and obvious. And so shown here is the full distribution of synthetic clusters as a function of age and, most importantly, mass. So shown in black are the synthetic clusters that people were able to detect. And then shown in red are all of the synthetic clusters that people missed. The blue line here shows the 50% completeness mark. So things that are above this blue line are synthetic clusters that we detected 50% of the time or better, and things that are below this line are the synthetic clusters that we missed more than half of the time. Once we have a good sense of the clusters that we are capturing with this citizen science, we're able to finally make our final catalog. So in this galaxy, this triangulum galaxy, we published this paper discovering over 1,300 new star clusters. These star cluster catalog was then used in a wide variety of science projects, both that I led, like the cluster mass function, initial mass function, which is basically how big the individual stars can get, as well as some projects that some other people led, which is the correlation between the H2 regions, the gas, and the youngest stellar populations in here. One of the science goals that I think is the most motivating and the most applicable to Andromeda, and the reason why I'm really excited about the cluster search in Andromeda and getting your guys' help, is this science result right here. So shown on the x-axis is cluster mass. So things that are on the right-hand side are very massive clusters, and things that are shown on the left-hand side are very small clusters. We see a straight line fit this function very well up until this green point, when it kind of falls off here. This is called a Schechter function, or a truncation of the mass function. Now, interestingly, we found that this truncation aligns perfectly with the star formation rate of the host galaxy. So this is a very nice correlation here between the star formation going on in the galaxy and how big that galaxy can make star clusters. Galaxies over here can't make super big clusters. Galaxies over here can make very, very big clusters. This is an awesome correlation. However, all of the galaxies that are up here, we cannot resolve individual stars. So that means that within a single pixel, we see tens of thousands of stars. And we may only be able to detect one cluster in a single pixel, which means that the identification of clusters in these galaxies is really hard. And also measuring their ages and masses is even harder. So we see really big error bars up here on the galaxies up in the upper right-hand corner, with smaller error bars down here for galaxies that we can resolve individual stars. But now we have an entire galaxy with its own environments. So as we begin to kind of zoom through the galaxy here, we're going to see different galactic environments in different local star formation rates. So here in the bulge of the galaxy, we're seeing a whole bunch of very dense red stars, so very old stars. And all of this dark area is dust that we can't see through. Dust can help cool gas and potentially lead to new star formation. So maybe there's some star formation going on in there. As the camera continues to pan, we're going to come to one of the largest star-forming regions in the local group. And so if that plot that I showed on the last slide is correct, and we go to an extremely highly star-forming region, we should see massive star clusters. And we should see clusters that are bigger than in other parts of the galaxy. So all of these blue stars here, these are very young stars that are parts of maybe some clusters. In this region of the galaxy, we expect to find between 2,000 and 3,000 new star clusters that have never been discovered before. And there's also going to be background galaxies that we're seeing through the plane of the galaxy, and entire galaxies that have never been discovered before that we can now see for the first time. As the camera continues to pan, we're going to come to M32 here in just a second. And we can begin to analyze all of the region around it, maybe some star clusters, and begin to piece together this puzzle of how M32 interacted with M31. And so looking through each of these images is an incredible opportunity to be involved with science and look for the first time at some of the most amazing images that we're able to produce in other galaxies. So here's the fast region. I want to find some star clusters, and I hope that you help me. Here's a QR code which is linked to the Zooniverse project. You can also Google zooniverse.org or local group cluster search. I personally think it's a little bit easier to perform the classification and the clicking if I'm on a computer and have a mouse instead of on my smartphone, but you do you. I'm extremely excited about the prospects of discovering new clusters in M31, and I'm really excited to be able to share this with you. I hope that you guys take a moment, and even if you just perform a few classifications, that will help our project. And you're able to contribute to science. So especially in today's day and age when science is under attack, contribute to science. Help us perform the task of science. Thank you so much. I'd love to take some questions. Yeah.
Two questions. One, do we get the name of clusters we discovered? And two, what role does dark matter have in keeping these clusters gravitationally bound?
Great. First question. If you discover a cluster, do you get to name it? If you want to name it fast cluster XXXX 1, 2, 3, 4, 5, 6, 7, then absolutely you get to name it. What role does dark matter play in keeping star clusters gravitationally bound? That's an excellent question. As I mentioned, what goes into making something gravitationally bound isn't something that's entirely known right now. I'm performing a bunch of different simulations and trying to quantify that exactly. Overall, on a galaxy scale, the dark matter halo is very prominent on a galaxy scale. But on a very local scales, dark matter isn't very prevalent. So you're talking about the density of dark matter not having a huge gravitational impact on very small local scales. So we don't think that it contributes meaningfully more than, say, the radiation pressure of an accreting star in the cluster. Yeah.
Is there a certain number of stars in a cluster? Like, how do you identify them? I don't know. How big is it?
Great question. The question was, is there a certain number of stars in the cluster, or how big is a cluster? Also something that is not well known, because we don't know what makes them. So we don't necessarily have a minimum mass, but we do think that a minimum mass exists, right? You can't just have 3 stars that are orbiting each other that stay together for a very long time. Typically, if I go back a little bit to my this plot here, this is a log scale. So this is where we made our cutoff for the Triangulum galaxy, which is 1,000 solar masses. So if you take 1,000 solar-like stars, that would be the mass of the cluster. So not all stars are 1 solar mass. There's a lot more smaller stars. So I would say probably of order 5,000 to 10,000 stars are in each of these clusters here. Yeah, back there. How much hydrogen do you need for a star to form? Very excellent question. So in the simulations that I have been running, in order to form something that is gravitationally bound, you need of order 100,000 solar masses worth of gas. Star formation is a very inefficient process. Only about 10% of the gas in the cloud will go into stars. So for a cloud that is 100,000 solar masses, only about 10,000 solar masses worth of stars will form. Yeah, back. Hat. How do you learn how to accurately identify a cluster? Excellent question. Very glad that you are extremely interested in being a good contributor to the project. One of the ways that we believe in this kind of growth mindset, we think that helps, is I mentioned the synthetic clusters that we inject into the images. When you find a synthetic cluster, there's a pop-up on the website that says, "Congratulations, you found a synthetic cluster." And so then users can be like, "Oh, hey, that thing I just clicked on, I'm going to click on more things that look like that." And then you can, kind of deduce, I don't know what's going on. Yeah. Yeah, so the question was, is there any kind of distance threshold on the star clusters? So, yes, this has to do with gravitational physics. In order for something to be gravitationally bound, it has to be within a certain radius of the, and it depends on the mass that's enclosed. So for a smaller star cluster, they have to be tighter together. For a bigger star cluster, they can be bigger just because of the amount of gravitational potential holding the thing together. Does that, okay. Yeah.
This is kind of answered a little bit, but so when you first figure out people's weights and stuff, how do you use like laser known sets? You give them all that first, and then give them kind of unknown clusters, or?
So this is all done after the fact. So you will go through, look at all 2,000 of my images, And then I will determine how good you are and assign a weight after that.
Yeah, I heard you describe a number of assessments as the dominant weighting factor there. Are you gathering any other information that also seems to have a deterministic feature for their success rate?
Yeah, so the question was, are we gathering any other information on the users that will help us predict whether they're good at performing the task? So really the two metrics that I showed on that graph are two metrics, but we weight them in different ways. So I'm actually going to go back to this spot. I'm going to scroll back just for a sec. Helps if I hit the right arrow. Help. Yeah, I need help. Oh no. Now I really need help. Slideshow, please. Thank you, Sam. The Uentas. All right, now I hit the right arrow. We're going in the right direction. And the question was on this slide. Right. Yeah, I can show it here. Right, so we have a couple different ways of weighting people based on these two different metrics. So people that are up here in the upper right-hand corner, they're not clicking on anything if it's not a star cluster. So if they don't detect something, it doesn't mean a lot because they're not clicking on a bunch of things, right? But if they did click on something, then it's maybe a star cluster. Whereas people down here, they are clicking on everything. So if they click on something, it doesn't really mean anything. But if they're clicking on everything and then they don't click on something, then that tells us a lot about that object that they didn't click on as well. So these are our only two metrics, but we kind of play around with them in a variety of ways. We have a couple different functions which messes around with them, and we can put that way. Yeah. What are the input variables for my simulations? There is a 25-page paper on the archive, which if you come into my office tomorrow, I will show it to you. Cool. Any other questions, last-ditch experts? Awesome. Thank you guys so much. I hope to see your usernames on Zooniverse.
We can get another round of applause for both our speakers. Amazing. I'm actually going to ask one of my friends, can you put on the nice picture of Andromeda? Just put anyone you like. Sick. Okay, so who has been here with us for a while and notices a difference in quality of our projector? Anybody? Yeah. Okay, so we're actually using a projector on loan because we wanted to see what type of projector we might need. And so does everybody agree we really like this type of projector? Okay, sick. So we're still taking donations to our little page. I don't have the little guy up there, but we are actively working on getting a projector as awesome as this one. So if you'd love to donate to us, I would love you forever. And also, just for funsies, it's our 10-year anniversary as of a month ago. We've been doing this for a long time, which is really awesome. So we just want to thank you guys for your support and just coming out every month and being with us as well. So thank you to you. Okay. I shall release you soon. I just want to say that our next Astro on Tap is May 28th. We have the amazing Tom Wag talking about a galaxy of binaries, and myself. I will be talking about how space is a soup and I'm a fork. So with that, if you want a prize, come see me. I have stickers and fun things for you. And with that, we'll see you next month.